downscaling. So I hope that you will enjoy and you can ask the questions in between if it is necessary. Otherwise, we will have a 5 or 10 minutes break between the two talks so that you can have more discussion. I think we will have a tea break. After this talk, we will have a tea break. Okay. So it is, I mean, two talks together. You can have a lot of discussion with him mathematically and whatever you. He's a mathematics professor in IIT Kanpur. Okay, sir. So now it's up to you. Start and.
So thank you very much. Thank you very much to both to Adway and Bipin for inviting me to be a part of this event. Recently we got into this area and we started exploring a few things. And so let me share some of the things which we have learned. And apart from that, I think since this is a workshop, I think it's good to get a little more insight into what's exactly happening inside the methods. So what we do is we will take 2 steps backward. Maybe it may be a recall for many of you. We will try to understand clearly what is downscaling. And we'll try to go over various approaches for the downscaling and what are the advantages, disadvantages. So we'll look at it. Then we'll look at one of the very recent methods, which is FNO, Fourier neural net for super resolution. So we are experimenting a bit with that. And I will also share seemingly some advantages. Of course, the literature says that there are quite a few disadvantages too. However, I think it would be nice to get a little more than the formal look at that. We will try to go, of course, in a couple of hours, we'll not be able to go very deep. We will try to learn a few things so that the take home will be a little more clear to us. So firstly, we will try to understand downscaling. We have looked at downscaling in several different talks, and probably most of that focused on the results. So here we will go one step backward and try to also look at the methods. And from the image processing point of view, essentially, if we to look at it, it's all essentially playing with the images. You play with the images either using image processing tools, or you play with them with different kinds of tools, whether PDEs, or you can also use neural nets, which is challenging. Of course, I would say PDE is better, but you may disagree with me. But I will have a say on it. The PDEs can do fantastic job, which you may not be able to get with the neural nets because it requires a lot of data. But that's not the focus of this topic. I'll leave this point so that you can discuss with me later. Why did you make a comment that PDEs are better than neural nets? Because we have come up with some methods. Seemingly, if you have a single data, I want to make a concrete conclusion. ML methods may not be helpful, but PDEs has got such a rich theory in it, and it can help you. But that's a punch point which is not going to be discussed. That's for you and me to discuss later. So that I think we'll have a reason to talk. So we will be, maybe I'll be able to share something so that you can look at that. Of course, you can solve PDEs also using neural nets. So in a way, it can come, but it's based on PDEs. That's also not the focus. I think you also heard something about the pins and so on. We will not worry about that. Here and there, I'll make some comments. We may not be able to go in a detailed way. So the outline of the talk is going to be, we will get into, of course, the introduction, and we will look at a little more detailed introduction into the topic of super resolution. That's a very general topic. So we need to really understand what super resolution means. We will start off from the image processing perspective so that you know the generality of the method. So one of the applications of this super resolution is downscaling, and this. It's widely applied in a number of several domains. So whatever you do from the methodology point of view, that will be applicable to a number of domains. So this is only a case where we say climate, atmospheric sciences is one particular application or application base where you can apply. But in general, if you were to look at super resolution as an image processing tool and as a methodology, you have a general tool which can be used in a number of things. Anything that you do to the tool will definitely have its impact on the applications from various domains. So since this particular workshop is focused on atmospheric sciences, I will probably not deviate from the application point of view. I will focus on the atmospheric science applications. But then we should keep in the mind that if you want to do anywhere images, but some neural net or something is not working fine, because if you look at it as a black box, you're done with it. But there's something, if you go a little more into the black box, you may be able to play. That's what I think several speakers were also trying to say, And if you were to look at different kinds of the neural nets, nothing but going a little more deeper into the neural nets or the machine learning methods and trying to play with the methods and trying to be a little more careful about these methods and maybe a little innovative on this. So I will try to highlight these points because the students and postdocs are sitting here at different levels. Maybe some of you already have an idea, some of you are new to that. So we will have to look at it. Where can I really improve my application results, whatever I get from this? Can I only look for every time a method fails? Should I always look for another method to come up, or can I go and do something more? That's always the research like, correct? So I will also look at, we'll go to the fundamental level of what is the basic atomic level, what a machine learning algorithm, especially in the context of deep neural networks, is what you can do at an atomic level. So for that, we have to understand how these atoms are built. We will also get a glimpse of these atoms, and we will try to see to what extent the various versions of neural networks that seemingly various different names, which I'll also be using so much jargon, nothing but little more understanding of an atomic level. When you actually practically translate it, it tries to give little more better version of the existing methodology. So we will try to, so we need to get a little more into the details. So we will, I will focus all the things in the context of super resolution. However, try to go little out, a little deeper when it comes to the methods. So we'll look at the introduction a little more in detail, and we will motivate. We'll also look at the applications, general and particularly to atmospheric sciences, and we'll get motivated in the context of atmospheric sciences. Why do we need to really look at these super resolution? Then we already had a lot of examples, but we will try to motivate it from standard benchmark examples that we come across in a day-to-day life, and then that will help us to be better prepared to accept the ideas or debate on it. So we have to debate because we are learning and need not accept everything. We can debate, question, that's what research is all about. And we will try to get motivated and look at super resolution in the context of atmospheric science. We will look at that and then try to look at what exactly these methods are doing in a slightly mathematical way. What is super resolution as a model? What is downscaling as a model? So far we have just seen a network coming up and some output coming up, but what is actually sitting in it? If you look at it mathematically, probably we'll get an insight that you may be able to come up with a better core, better cuts, which will be the life for it. And it can, in turn, help us to use all the tools that we have learned in our schools and colleges. They'll become very handy in coming up with basic networks improvements on that with a firm mathematical understanding. I just give you a glimpse. We'll not be able to go into the great depths of this. Then we will look at a few of these methods and ML and DL methods. Both of them will try to give a little bit idea about it. Then we'll go into super resolution and there's some case studies. Then we will, having done all these things, we will be building a case for the latest, one of the recent ones, last 5 to 10 years. Last 5 years, I won't even say 10 years. Fourier neural operators have been in talk across the world. It has its own plus points and minus points. Don't take me straight away. They're already shown that in the context of atmospheric sciences, they may not be the best ones. Already, I think Professor Chatterjee was just mentioning that swin IR is one of the promising things. I do agree. There is a comparison of swin IR with Fourier neural operators, seemingly good, seemingly bad. So it's still at a stage to weigh it up, but FNOs have a great promise. Which other methods seemingly need to compete with that method? Maybe it may have. So I will leave that punch point, why it has got a promise. Seemingly, we will also try to highlight that as we move along towards the end. I hope I will be able to cover all these things. So firstly, by the way of introduction, we will look at super resolution in image analysis in a very, very general perspective, and then we will move to the atmospheric sciences in particular. So we all know that super resolution is a technique to enhance the spatial resolution of an image, making it appear as it has been captured at a higher resolution. So you actually take the image with minimal resolution and you try to take it as if it has been captured at a higher resolution. So that's a very naive way. That's how we can put what a super resolution means. So how can you actually transform something which has been actually taken at a low resolution to the high resolution? What are the various methods? That's what is the super resolution methods. So there can be several different approaches for that. So it is a computational approach, super resolution approach, because this is applicable in all the domains. It's a computational approach because you already taken in some amount of data at a low resolution. So you're transforming that data computationally. It could be called as increasing the pixel density. If you were to look at it, where exactly something different is happening, you look at it in the super resolution, the pixel density of an image while preserving and even enhancing the sharpness and the clarity of the important features. That should be the important thing. You cannot alter while changing the pixel density. You cannot move away from the original image. You have to maintain, it should be invariant. Information that is there should not be lost. So how does it actually guarantee us? We will look at it mathematically, and then we see when it is transformed into operations, what exactly is happening. We will have a look at it. So it is intended to transform. You have a low resolution, you have maybe have a blurry image, not so very clear, fuzzy, or it may have unrefined details. So the high resolutions, you will get a clear perception and a clear idea of with enhanced details. So this is what it should do without losing the original context and the image of the image. So that's a typical cartoon. What you see here is the original image. That's a degraded image, supposed to be. If we were to take a structural symmetry metric of these two things, you'll find they're distinctly different. It's going to be pretty low for that. It's going to be structurally quite far from this. It may be difficult for it to say a typical cartoon which is used. And that's used typically super resolution convolution neural network. A standard example, a benchmark which is used for just saying what is super resolution. If you take a structural symmetry, take big pixel comparison of these two things and find out all the intensity, that's what essentially structural similarity means. If you take and then sum it up, structural similarity between these two would be fantastic, whereas these two will be less. Given this, you should move to that using what is known as a super resolution method. So that's, so given a low level image, low resolution image, we would like to move to the high resolution image, which is structurally very close to the original image. So that's what super resolution in a very, very naive way means. So let's look at some of the standard benchmark examples. So what you see here is a cartoon. There's an image, and we have a calendar. If I were to ask you to read, probably you need a lens to zoom it up and see it, and it is not so very clear. It's a blurry. So different super resolution methods. I will also get into these methods because this is a workshop. We need to understand various terms. We will get into these. So different methods have been used to improve this small patch. That's these are all the things. At least in these things, you are able to see in the final patch, which is a ground truth. This is what it should be like Tuesday and Wednesday from what it is should be. Which of it is going to improve it? So in one of these things, this is a cartoon which I have picked up. It is not a result which I have produced. And then what is in this cartoon? This seem to be structurally more close to that. So now this is another cartoon. What you see is a lot of skyscrapers here. In this, what is exactly sitting here, you want to get the finer details of this, you need to really enhance and go to the super resolution level, take this low level information and try to get to the high level information, and then try to see, can we recover, given this, can we recover as much as possible what is exactly the details of this. So these are all number of different methods. Let me first show you what are these methods and come back to this slide again. What I've shown you is you have a two-flow, you have a RCAN, you have a FR-VSR. These are all the standard acronyms. We don't need to worry about it. If you just Google it, you will immediately get all these acronyms and explanation. Two-flow means a task-oriented flow, and FR-VSR means frame recurrent video super resolution. I've also given all these details here for somebody who's interested. We'll be able to see where exactly, when was this actually talked about for the first time or more seriously. So DVF is deep voxel flow. So the algorithms and the details of the methods are all in these papers. So different methods have been used to improve the quality of the low resolution image. This is a standard thing, and then try to see which of these things are going to be really better. There are metrics. We will come to metrics subsequently. These are all the motivational examples, cartoons, or standard examples there. There's another very nice example. This is what is the low resolution image, and you would like to really recover all these fins which are coming out nicely, and different methods are used here. And the SR phantom, this is the original low resolution image. And what you see is different methods are used for recovering. In this case, conventional methods like filtering has been used, filter out unwanted data, noise, and blur, etc. You try to recover. So what you see here is PSF, which actually means point spread function. That point spread function is used for taking this image. Conventionally, what they do is image process it by using different filters. So one of the standard filter is box point spread function box filter or the uniform filter. What is actually it means? It tries to convolve the image data window by window by a convolving window, which is going to be, you're going to have a mask of this kind, you're going to convolve with this, and you slide it out and try to improve this image, given this low resolution, and try to remove the unwanted things. You filter it out, use this as a filter, and this is a uniform filter because everywhere there are uniform weights. Therefore, box point filter or uniform filter is a standard filter used for improving the image when it's a low resolution try to get. So if you use this is a box PSF is one of the methods here. Box PSF is the D, image D. If you use this filter and try to convolve this and try to improve this, the kind of the image that you get, that's moving from low resolution to high resolution. And you also have what is a Gaussian PSF, which is a Gaussian point spread function. So here you're going to use a Gaussian function to try to filter out the data, and that kind of the filter that it would actually be is going to be this. So these are the entries which are going to see. What you see here is a bell-shaped function. More information around the center is going to be taken. So that's where you have higher values here and the lower values down. And if you use that filter, this is the E is going to be from the super resolution with a Gaussian PSF point spread function. So these are conventional approaches for improving the images. You can use these images even on the kind of the atmospheric data and try to see if it's going to do that. But it has got its own pluses and minuses when it actually goes for the application. These are typical image data. So you use these methods. These methods can be used elsewhere too. And this another last cartoon which you see is you have a nice cartoon of a mosaic, a set of mosaics, and you would like to know the subtle details of this. So what is given here is sample low resolution image of this particular mosaic and the estimated super resolution of this mosaic. You see, this is what the low resolution, the estimated one is this, the original high level image is this. So given this, you would like to go here, and what the methods would do is actually something like this. So given this low resolution image, would like to recover this where the details are more fine.
Better than the ground truth. I saw the other one also, calendar. Better than the original.
Maybe. Yeah. So this is, given this image, maybe just got a high resolution, make a comparison. In this, these are the benchmark cartoons, not generated. And
calendar image 31. That is better than the original.
So that's what, say, the conventional methods we should not forget. These are all the, so jumping into the state-of-art methods, forgetting the conventional ones may not be good. That's the message you get slightly as you pointed it out. So maybe hybrid methods are used where the conventional with the state-of-art methods are used, wherein whatever you can use in some contexts, you'll be able to get better recoveries. Hybrid methods also proposed from the point what Bipin is saying. You could also think of, if you look at this, these are all standard benchmark examples, which are from the books, that this is what it is. So that shows that don't forget the conventional ones. Gold is always gold. Maybe somewhere it is going to be handy when the things, you don't have to spend so much of energy to really come up with a new method when it's really not working fine. Maybe try out, don't forget the old ones. So that's what is the message. So super resolution, we got a naive idea right now. I am not going into too much of details. And why should we know about the super resolution? Of course, I've shown you a few cartoons and said that they're all very interesting in this context. And that's not the only context. It's in the context of the applications. Yes, satellite imaging, biometric information, identification, medical imaging applications, and earth science, earth observation, remote sensing, a number of other applications. You have a microscopy imaging, image processing, surveillance, and multimedia industry, video enhancement, astrological studies. So wherever you need to have a clarity, even it is used in the health for MRI images, CT images, which are used currently, the techniques that you learn, the methods which people are talking, they are also applicable in the health industry. We may be interested in the health, atmospheric sciences, but that's why I wanted to highlight generality with the mathematical method, which is sitting at the core of it. And a lot of mathematical research also goes there. I leave it at that. I will highlight that point and leave it for you to see what I can do. Okay. So why super resolution is important for atmospheric sciences? Now, this point I wanted to say more from the context of atmospheric sciences and say that in the context of atmospheric sciences, what it would actually do. Of course, we have an understanding. Maybe it's good to recall. So a limited resolution of the current satellite and aerial data is a well-established fact. You will not, if you can get everything from a satellite image, nothing to worry about it. You get a lot of images which otherwise you cannot get, but that information may not be rich enough. So because of the limited resolution, so spatial resolution people are currently talking about a pixel can be covering 1 kilometer range. So a pixel, whatever is the images that may be covering 1 kilometer of the satellite image, whatever you have. So, but if you want a more detail, subtle detail, in 1 kilometer, how many buildings can be there? Can be many buildings. If you want to have a subtle detail, probably you may have to go to half a kilometer, even less than that, and maybe get the finer details. So super resolution probably will be a way to get that information. So especially, and also in the cloud formation, I think there was a talk on the cloud formation. If you want to have storm dynamics, etc., pollution dispersion, which we saw the other day, limited resolution may become a hitch there, and we may use super resolution methods to improve. Same thing happens again with the temporal resolution. So if you have a satellite sending us images, we know that satellite frequency once in 5 hours, once in 6 hours, once in 24 hours. So you can also do the temporal super resolution, temporal resolution, which is also a topic which people use. So using this periodic, we know the satellites often revisit the same location on periodic basis, daily, weekly. So temporal resolution also is an important thing, and we have to have a lot of reliability if you have a temporal resolution being built in. So you need to have a lot of data which you validate. If you just, so you need to have, if you have a temporal resolution being established, so you need to have data of several years back, and then so that your methods, the temporal resolution is also going to be fine, can be really talked about. Mostly that we have addressed is spatial resolution in various discussions, and temporal resolution discussions is, there are papers on that, and that would be a very interesting topic if you were to look at it. So the detailed atmospheric modeling. So that's very important. That's why the challenge of going for high resolutions in terms of global weather predictions, GCM models, whatever you have. So it's a challenge always to ask for more and more compute power, more and more memory to get the finer details. So atmospheric sciences relies, as we all know, on accurate representation of weather and climate phenomena at very fine scales. If you're actually looking at some turbulence phenomena which is taking place, you need to really understand the energy cascade, the momentum exchange. You need to really go into the fine scales. The fine scales, what you need, may be very demanding. So without high resolution imagery, important details may be missed out, and it's a challenging always to have a high resolution imagery. Therefore, go for simulation approaches. SR will be super resolution methods can be one viable way, provided you have a lot of validation done and reliability established on your methods being used, then you will be able to use them to get some idea. So atmospheric phenomena as such is very complex with fine-grained features and small-scale weather patterns and cloud structures and pollutant hotspots. If you want to really identify these things, then you need to have fine resolutions. So application to operational weather forecast, we see that the super resolution can transform operational models for providing high resolution inputs. So operational models, if you want to really use the operational model for forecasting, so you want to be very, very correct and precise, super resolution models will be very, very handy there. So in the context of storm forecasting or understanding the wind flow dynamics in the mountainous regions. So this is a particularly interesting problem, especially in North India, one region where the Chitrakoot area, a lot of the cement factories are there. There's a region which between the two mountains, there's a heavy circulation of pollutants. They're really trying to find out what should be the way, and understanding the subtle dynamics of that is a challenge even today. So a lot of atmospheric meteorologists are looking at it from different perspectives, and super resolution can be a way out to understand some subtleties which otherwise are not understood, and improved detection and monitoring of climate change. That's definitely requires super resolution. So high resolution imagery can definitely help understanding the vegetation, change in the vegetation, changing vegetation patterns or deforestations. So these are all the things which are very, very important applications where this can be there. Yesterday we saw that advancing in the air quality monitoring. So super resolution again becomes a very handy tool for air quality monitoring. If you want to get a precise maps of pollutant concentrations in cities or industries, which may be in less than half a kilometer range, so you need your satellite images, whatever, it's 1 kilometer per pixel. So if you want to use maybe super resolution method, can become handy. So Now let's look at typical example from research works that what people have looked where super resolution already been found to be very, very useful. This is an example of how the super resolution helped the low resolution images related to the air temperature at 3 meters and air temperature at 43 meters and wind velocities in the terms of W, U, and V components. So let's look at this. What is that? This is the kind of the ground truth. The low resolution image that you get either from the satellite imagery, this is about the temperature, is something of this, and the super resolution methods have taken this information and are able to regenerate this information which otherwise the images did not have it. So that's the ground truth. So this is at the height 3 meters. So you need to have a gradation of heights. We know various spheres, if you want to troposphere and different spheres, if you want to go from the surface of the earth, you may have to see that your methods are robust, not only on the surface, it's also robust enough at various levels from the surface of the earth. So this is the 43 meters. This again seems to be, this is information from one of the recent papers. I'm just showing you to convince that this is used currently, super resolution used. This is the image that you have as a ground truth, and you will be able to use the super resolution methods to get better information or high resolution image. So now what you see is the wind velocities in terms of U velocities, and this at temperature height 3 meters, this is 43 meters. What you see is the V component of the velocities here. Super resolution methods are there's a W component. So that's the kind of the utility that super resolution is being used to the basic, what is underlying methods as basic image processing tool is all that is being used here to recover what the information, otherwise you do not have the image processing through the super resolution techniques. It becomes very handy. This is from a paper. Sorry, I missed the reference there. Maybe towards the end, we'll have a few references coming up there. So let me also give you another convincing example. This is one of the from the recent papers over the North America, where a low resolution image is given using the super resolution of the surface temperature. This you can go to high level, high resolution, and we will look at some of these methods. First, these are motivational examples. What you look at is here you have net surface shortwave radiations. This is what is observed, this is what is caught, and that's the super resolution method will give this from this information. You will be able to transform this to this, which has got a lot of information that has already been validated. These are the outputs from the validated methods. This is only the examples just to motivate us. This is that's for the shortwave radiation. This is for the long wave radiation. So you have the radiation physics. It's a challenge to get clear information about the short and the long wave radiation information, and you are able to get, again, super resolution methods can be used to have, given the low resolution information, you'll be able to go to high resolution levels and try to recover a lot of this. Also regarding the large scale precipitation data, I think there are a lot of examples which have been shown. I think you will get to see more of these examples in the subsequent talks. So these are some motivating examples that learning super resolution methods is useful for atmospheric science. So that's some examples are benchmarks from the textbooks. Some examples are from recent papers. So it goes to say that this is worth looking at. So what this methods actually is looking, what is this method mathematically all about? Let's look at that. So super resolution method as such is an ill-posed inverse problem, and why it is ill-posed, why it is inverse problem, we'll get to understand. The method, very briefly, can be described as y equal to h of x. Given a low resolution image h, which is nothing but high resolution image being polluted by a lot of operations that it has undergone, there can be blurring, noise, etc. All these fellows are sitting inside this h, and this h has already acted on the original image, and what you have is y. So the y is all that is with you, and your challenge is now invert this guy h and then put it on the left side and enjoy your x. So, but this h is an ill-conditioned fellow. So this h is an ill-conditioned fellow, and therefore inversion of that becomes a challenge. So how do you deal with this problem? So given a low resolution information, which is y, so which is actually coming from a high resolution image which has been polluted, or various things has taken to that. That's a h, which is denoting. So x denotes the high resolution image, y denotes the observed low resolution image, and h is a matrix which can be a number of operations. So for example, it can be blurring, wrapping, downsampling, and various things can happen. So now you have to deal with this guy. You have to give a proper representation for this guy. And then look at it and invert it out. And that's what the methods do in various ways. So that's an ill condition. If we try to invert it straight away, we'll see that's going to be highly ill conditioned. So inverting that is going to be a challenge. That's what the various methods do. So having got an ill conditioned problem, so the challenge is, of course, if you're trying to do computationally or trying to recover what is this x, we will never be able to recover x fully. You're going to get only an approximate x. When you go and get an approximate x, how close this approximate x, which is x cap, is close to this, that's what we would want to get. Firstly, the challenge is that this is given an ill-conditioned problem. How do we solve it? So we have, lucky for us in mathematics, we know about regularization methods. So there are books on regularizations, and you need to just regularize this and handle this ill condition. So which regularization method, if I ask, I think some of you who are already mathematicians or who know something about regularization, so I have my own Tikhonov regularization, or I have TV regularization, or I would like to have Tikhonov plus TV, or I would like to come up with another resolution, another regularization. So there are lots of open problems, which regularization best, in which context, you will be able to come up with these things. So what is this? So that's what is recovering x cap through a regularization process. So this is what is a given problem. So I would like, we would like to, while I would like to find the x in an approximate way, which we call as x, by minimizing this functional in such a way that I don't lose my exact message in the process, in the image. In the process of trying to find the original image, I should not forget the image at all. So image should be, my original image should be kept. So that's a fidelity term, so that I keep track. So that's called the fidelity term. I would like to minimize, take this y, make this as small as possible, and regularize. Since this is an ill-conditioned fellow, I would like to have regularize it by using a regularization functional.
So this h and y previous, these are the matrix you are considering, the 2D matrix or
whatever you say, information, low resolution x. X is a low resolution entity. Y is a high resolution, sorry, X is a high resolution entity. Yeah. So your entities can be anything. It can become an image. It can be a vector. The way you process it in your methodologies, you can take a matrix and process it.
For the back slide.
Yeah.
Because it looks like a Ax kind of Y hx. So X looks like a vector and Y in H like a matrix. That's what I was.
Y equal Hx. It's an entity which can be anything in the context. If you want to look at it as a vector, you have your image, which is a matrix, you write it in the form of a vector and process it. You transform the whole thing as a vector form into it. So it can be a tensorial entity. Generally, you should look at it as a tensorial entity. Tensorial entity is a very general description of that, and you have two tensors being connected, and H is a tensorial operation. That's a general description. So if you have a general description, X can be a multi-modal data, X can be a single modal data, the way you have the image intensities, that it can be that. You want to have a tensorial entity, you look at it, that's mathematics, which helps you to look at any kind of a complexity. I have a data in terms of collection, I have a data in terms of images, I have a data in terms of satellite. So multimodal data, the X can be written out in a multimodal way, and you can homogenize it and then process it. So look.
In terms of the X, I wanted to know Y and H. So suppose X is going to be 4-dimensional.
You do it. So tensorial entity, you have what your H will also be accordingly defined. Of course. That's why I said you look at it in a general framework, tensorial, and it's finished. So it's a general representation depending upon, I'm just thinking of some entity in a context. If you have a simple context, it will be simple, just a matrix vector. In another context, if you said look at in a tensorial representation, it will be general representation. That's a general tensorial notation. That's understood. That's what I'm saying. I am there to tell that. Correct? I'm there to tell that. I'm explaining to you. That's a tensorial representation, which is very general. That's the power of mathematics. In mathematics, you can represent, generally encapsulate a lot of things in that notation. So if simply you want to be y equal to ax equal to ab equal to x or something, whatever, ax equal to b, yes, you be happy with it. And that's what you need to be that. That's the symbolic representation. Mapping of that in your context, simply ax equal to b. Ax equal to b is one particular context. Right? So I hope that makes sense. So it can be a general entities. We also have, yeah.
Next slide.
So what is the, I mean, mathematically of lambda Ex, I mean, why it should exist? I mean, what is the...
So this is what is, these are called as regularization methods. So the regularization methods tell you, if you have an ill-conditioned system, how you go about regularizing it and you're getting it. So the ill-conditioned system, if you regularize it, this is a regularizer which has been used. How you define the regularizer? The research work. The standard regularizer, Tikhonov, TB, these are standard ones. People do a lot of this. You can come with different expressions for this functional.
Suppose I want to take divide by lambda ex. Is that
What?
Y minus hx divide by lambda ex.
Well, if I can give an interpret, it is a fidelity parameter. So how you would like to define this parameter, it's okay, you can define it, but you should make a physical meaning for that. If you can, as long as you can make a physical meaning for the parameters, that's a symbolic notation. How you define it, how you physically, it is going to be acceptable. So for us, it is a standard. This is in the framework of a regularization functional. I have something, this is not working. Okay, this, I think I will use the pointer here. So what I have here is a simple functional, which is a fidelity term. You regularize it because this is H is an ill-conditioned system there. So therefore, this ill-conditioning is taken care by this. So what are the standard regularizers that we use there? I hope this is works. So what are the standard regularizers? So EFX is prior information, which is called a regularization term. So what are all the various possible things that you can get for EFX? Let me take to the literature. So that's called the regularization parameter. So let's look at some of the standard regularizations in the literature, in mathematics literature. You say Tikhonov regularization, you can have EFX being defined in this fashion. This is L2 now. So we all know that. What's that? That's a regularizer. Tikhonov as if you have a regularizer, its convergence, that this method is going to converge to the original solution, all that is well established in theory. If you're introducing a new regularizer, then you have a lot of mathematical problems open for you. With my new regularizer, it is going to have a convergent solution for which I'll be able to prove that everything is fine. So, or you can have a TV regularization, which is also very well known. These are standard examples, right? So you can also come up with physics-driven regularizers. You can also come up with new, so therefore the research comes into the picture there. What is the best regularizer? I think, what time I have to stop? 11:30?
What is working?
Point, no, this laser is not working. That is gone. So I want to tell, this is the first point. So if you want to look at mathematically the problem, you may have a chance to look at a regularization methods and find out what is the right regularizer I need to use in a particular context and maybe come up with things. So what exactly this becomes? This problem is nothing but a variational problem. Let me go back to this problem. Nothing but minimization problem. A variational functional that you have here, that's a variational term. That's a variational term. You have to find a x such that this variational entity is minimized. So EFX, you can either use a well-known or you can invent your own. Yeah. The ill conditioning is lost. The well-conditioned matrix will be well-conditioned after that. I smoothen out the matrix ill conditioning. So that's in a naive way. So I have a ill-conditioned system. I have methods to take care of ill-conditioned matrices. So this, in the functional form, the ill conditioning is taken care here. If I do that, the resulting matrix from this functional will be invertible. Otherwise, you have difficulties. You may have a 0 on the diagonal, or you may have very, very small eigenvalues. So you may have a clustered ones, you may have difficulties. So this guy is going to take care of that.
Even it is like a preconditioner?
Precondition, you can have a preconditional regularized system. Precondition, another approach. Precondition is another approach. So this is a regularization at the functional level. So I am not going to the matrix level yet. At a functional level, if you have a matrix level, if you have acceleration, to accelerate the solution process, you use a preconditioner. So you are even at an elementary level here. At the elementary level, by which I mean that you are looking at a functional and trying to handle the preconditioning the ill conditioning right at the elementary level. So when you pose the problem, you try to handle the problem at that level. That's what is at a primitive level here. So at that itself, you are talking about a level. Preconditioning is used for accelerating something. That is the matrix. So you take this and put the problem in the conventional AX equal to B, and then a precondition can be used for accelerating, right? So let me use, I think a cursor is not, this mouse is, pointer is not anyway. So now I want to highlight once again that you have a scope to come up with different regularizing methods. So that's a problem which it can be problem specific, it can be physics specific, and people talk of several new ways of regularizing. So I'll start the talk again. Thank you, Adway. So please tell me when I have to stop. I will stop that time, and then I think. Yeah. Sure. I'm very keen on talking of some of these things because it will help students to think differently and then also debate on it and then come up with various things. So that's where we are. So we can come up with different methods. We have some little naive understanding. I don't say this is too much of understanding, simple understanding of what is happening at a super resolution, what exactly it means. So mathematically you can come up, there are a lot of mathematics. If you come up with a new functional, you need to establish that it is a functional for which a minimization exists. You need to prove a lot of things there. So coming up just with an expression for EFX with some understanding will not be acceptable. You have to go back to mathematics and show that this functional that you approach has got a minimizer. So you have to get into the optimization world and try to do that. And that's where you should not blindly propose a EFX. For Tikhonov regularizer, and if you have TV regularizer, things are very well established. That a solution exists, that a minimization exists for that becomes a new question that we need to handle if you come up with different things. So these are examples which people use. And let me go to the, now before, since I have 10 minutes, let's talk popular. So we got mathematically what it's all about. So super resolution approaches are several. You will be, I think many of you know, it's good to recover the gallery of methods that exist in the, under the guise of super resolution, gallery of approaches. And then, so what are these gallery of approaches, super resolution images? So you can have interpolation based methods, which we learned from the school days, probably college days, bicubic, bilinear, nearest neighbor, line source, and the cubic convolution. You can have reconstruction based methods, host of them are the gradient profile, and TV regularizer, etc. You can have transform based method. You can have learning based methods, which is recently being talked, and lots of them. And each of the, and deep learning is one guy sitting in this gallery of approaches. So under our interest is ML, because the workshop is on ML, AML methods. So let's look at how many methods do I have in deep learning? Do I have 5, 6 methods, or how many? Let's look at it. So let's now focus on this guy, and let's look a little more in detail. How many methods do I have? Definitely, we need a course for covering all this. So that's why I said that we'll not be able to do any justice. Minimal justice also will be not able to do. But in a workshop, we should have an idea that what finally I'm going to do is a small pathway which I am following to the truth. So that small pathway, we will anyhow go to the small pathways, but we should know that there are so many paths for it. And just under this name, gallery of the methods that exists, again, there are so many subclasses of recursive connection methods, host of them. There are multi-branch connection methods, residual connection methods, densely connected methods, so on and so forth. There are so many. Well, to understand each, these are different architectures. Some of you must have heard of some of these things already. SRCNN, you will be hearing a lot. And you would have heard of many of these things already in your GANs already you heard. Generative adversarial networks, you heard about that. And what I have not added is FNOs. FNOs is a new thing which I will be talking about, so I did not add it here. If you have a gallery of this, and just for your, we can have these details of these methods, we will not worry about it. So what we will try to do is, we will go back to this, and before we launch completely onto this, it's very good to have an idea of some very well established methods, and then try to see these very well established methods. Do they work in the context of atmospheric sciences too? Should we only talk of deep neural networks, or should we also use conventional methods? Can we go for hybrid? So we need some kind of evidence for that, or experience from the people who have already looked at it. So it's good to look at some of these things. Maybe a recall, it's basically recall. So we will first start with the basic recall on the so-called interpolation-based method. So that's very easy because all of us understand interpolation. I think we study that in the colleges. All of us know what interpolation is. If you have small resolution data, interpolation is one way that you can get the intermediate missing point data. How good or how bad? There are the questions that we need to answer. So elementary kind of super resolution techniques are commonly utilized for zooming images by estimating the pixel intensities on upsampled grid. You have a low resolution grid, so you have a data available on it, use interpolation to upsample it to the high resolution grid. So that then you'll get from low resolution image, you move to the high resolution image. So there can be kernel, in this method, interpolation based methods, there will be permanent kernel functions like cubic kernel functions or local variance coefficients. In this particular method, which I'm going to show, that some of these tools are being used. So we'll have a quick glimpse in the next 5 minutes about this one particular method, which is one of the methods under the interpolation-based methods, before we move on to deep neural networks and the application of atmospheric sciences. So this is a bivariate rational fractal interpolation model, which is introduced in the context of image processing, which people also use it for in that context of atmospheric sciences. What does this do? You given a low resolution image, you first, from this image, you take out its texture separately, take out its non-textural cartoon region, which is a background, and the texture region. You take out the texture, and this is the first image processing, texture and non-texture region. There's a region division for this image. You do that. That's one of the first steps. How do you do that? There's steps involved, algorithms involved, processes involved in moving from this to this. From this, what you do is get pixel, divided this into patches of pixels and get the dimensions in terms, so get the dimensions of these to be very flexible. You go for fractal dimensions of that. Each of this can have a fractal dimension. It can be an integer, or it can be a number. Why do you need to do that? Is when you're scaling it, if you scale it to the dimensions, it will be very handy. So the fractal dimensions are used so that the scaling at a later level will become easier. So they used to have fractal dimensions for each of these patches. Fractal dimensions are defined, and that's what is the calculation of the fractal dimensions, which is taking place both for this and that, and used. And all this is at, let's say that you have it on a 5x5 patch with all this information you have. This is a next step in the algorithm, which you need to really work it out. And now you take this information with the right dimensions and the right scaling, you interpolate it into a finer grid. So 5x5 into this, you can use a bivariate rational fractal interpolation. The fractal is coming because it's taking care of the dimensions of each of these small cells in terms of the fractal dimensions. And you just get the highly interpolated data here. So you could have a factor 2, you could have different factors, and then you map that information into this. So original image. So all along when you do this, carry this information the way you through your mapping functions, you'll be able to generate from every patch which is 5x5, which has been taken to 17x17, and all the patches are now worked upon, and they will get a high resolution image. So that's a quick look at bivariate rational fractal interpolation method, and this method also works in the context of atmospheric sciences. So that's just to show that this method is an image processing. In the image processing literature, you'll find this, and you get to see the subtle details. So these are the different methods which can be used for doing a super resolution of the images. So what you get to see is for the different methods which are there. So the images, the way they have been transformed, that's what is there. And these are the names of some of these methods. I think these are very methods starting from 2000s and quite recent methods. There are several different methods. So these are the name of the methods that what is being done. These are standard, well established methods. So you will be able to use based on the idea of interpolation, bivariate, fractal dimensions based interpolation is something innovative, and you can get to see the performance of this method in terms of these metrics. Feature similarity or structural similarity is one very standard metric. Pixel by pixel comparison you make and check out what all the intensity is there that the feature, or the peak signal to noise ratio is another, and SIM is the structural similarity. So these are all the definitions of these metrics, the way you can calculate the metrics based on the image. And you see for these various methods, the bicubic interpolation, other method, which is the gallery of the methods, which I have shown, these are all used for this particular data cartoon, and kind of the performance that you get for twice 2x and 3x super resolution, the way the various methods perform. So is given here. You find that bicubic methods are quite promising. So that's the fractal-based method, which is bivariate, which is there currently discussed here. This seems to be promising in this context. So there's few other examples in this, using the same approach, where again, we will be looking in the weather context, some of these methods, bicubic, and you have SRCNN, super resolution convolution neural network, and other methods. So again, you are trying to compare various methods, and these are the various methods that are listed out here, and these are papers where these methods are discussed, and you will get to see that these conventional and state-of-art methods, they are working quite well in improving the information hidden in the image. So either I should stop here before we go into, stop here. So now in the next, what we do is we will get into the deep neural networks. I've given you basics of super resolution, go in deep neural networks, have quick glimpse of deep neural networks, get into Fourier neural nets after that, both from the deep neural networks and also from Fourier neural operators. We will look at applications from atmospheric science. Okay, I think if there are any questions in this, I think we will.
Yeah, if we have any online question, we can take, and for you people, you can discuss it during the tea time.